So, welcome to another MTH218 class. So, this week the plan is to look at double integrals over more generic regions. We looked at rectangles last week. But just before I do that, I just want to look at the assignment. So, all the assignments have been marked. I hadn't released marks just yet. I will do that tomorrow once I've just moderated everything. So the marker though has flagged that lots of people did a great job, which is awesome to hear. So many great results. The two questions that people struggled with the most, I just want to cover right now. So the first of them, which is intended to be difficult, so that was certainly the intention, was the level surface question. So this is certainly the intended to be the most difficult question too. So you've got a function of three variables given by a fraction here. Chosen this way is at the bottom is never zero, so it's always well defined at least. And you have to try to draw it in 4 dimensions if you try to capture it. So that's a bit beyond all of us. And so the way to try to understand the function is to break it down into level surfaces. So look at what this looks like for fixed values. So I'll focus mostly on what B is here. And so the level surfaces pretty much have the form, the function is equal to K. That's what the basic form is. Now, by some observation, because it's all squares on this side, we know that K is going to be 0 or positive. So we can cut a few options down, but that's what it's going to look like in general. I want to try to understand this as a surface now. So now I've fixed a constant, so K will be 0, 1, 2, 3, whatever it might be. That's now just a surface, no longer something seen in 4 dimensions. So we've dropped a dimension down, which makes it a bit easier. So the first thing I would do is simplify it down. So just clear the fractions pretty much. And I gather everyone was okay with this part. So something like that. So just get rid of the fractions, put all the x, y terms on one side. So x squared plus y squared minus kz squared equals k. And so now we've simplified. You go, hold on a sec, that's just all quadratic terms, so it's going to be a quadratic surface. It might be different surfaces depending on what the value of k is, but they're always quadratic surfaces. So again, let's take different traces. So if you fix x or y, so in both those cases, you're getting x squared, a difference of squares left over. So that gives you your hyperbolas. Oh, let's be more precise. I mean, I should spell this out. So for example, you'd get, if you fix x, you get x y squared minus k z squared is equal to a constant. So you fixed x, you get that sort of thing. Now, most of the time that's hyperbolas, so long as you actually generally get a difference of 2 squares. So long as the k here, this coefficient, is 0, is positive. It's got to be strictly positive. If it's not strictly positive, it doesn't work. So k equals 0 makes things funny. So we have to really treat that one separately. So if you've got, as long as k is on 0, sweet. And then if you trace in the other direction, so take a step back. Since you've got 2 directions fixed by hyperbolas, it's going to be, in general, a hyperboloid. And work at the 3rd direction, works out the type. So if z's fixed, then we're getting x squared plus y squared equals k outside of 1 plus z squared. Now, if k is non-zero, 1 plus z squared is, well, certainly positive because it's a sum of the squares. So that's always positive. So these are circles, or ellipses if you want to say it, with no breaks. So again, if k is non-zero, then these level surfaces are hyperboloid with no breaks, so hyperboloid of one sheet. And again, so before I wrote the k equals 0 case, what's similar and different about them? Well, pretty much they all, so the same center, so they all have the center of the origin. Indeed, they have the same central axis, so they all going to look, so the pictures are going to be the same. The only real difference for them all, so the same central axis, which is pretty much the center of these circles here, which is the z-axis. So all these sort of pictures are going to be the same. The only thing really is different is just the scale. So the scale for x and y will change. So to give you an idea, let's so the hyperboloids of one sheet, so you get a nice circle in the middle, so it's a circle of hyperboloid of one sheet even, looking something like that. Harder to draw is the normal, normal being a piece of paper. So that's one example one, so k equals 4, say, just as an example one. The circle that fits in the xy plane really is this particular circle for when z equals 0. So you notice if z is 0, just x squared plus y squared equals k. So if I pick k equals 1, it'd be a circle of radius 1 down the bottom. And I'm doing a really dangerous thing of trying to draw both circles at the same time. It's hard to draw, you think. So if you change the k, the shape, overall shape's pretty much the same thing, because it's still circular hyperboloids with the same central axis, the z-axis here. But what's happening is they're shrinking as k gets smaller, or getting bigger as k gets bigger. And the radius of the inside circle here is sort of proportional to the square root of k. And you can say that different ways, but so that's the key idea. The one thing we haven't really covered, and you needed to get full marks, which is perhaps the hardest bit, is what happens when k equals 0. So this is a particular level surface when x squared plus y squared 1 plus z squared 0. So if you clear the fractions, you can see that the z squareds all disappear. Sorry, I dropped out there. Can you still hear me? Yep. Okay, thanks. internet goes down. It's bizarre, isn't it? I'm in a nice LAN network and everything. Anyway, so what I was trying to say before I kicked in is when the sum of squares is 0, that really forces both the x and the y here to be 0. So pretty much when k equals 0, really you're left with the case, which I can draw, is when x and y are both 0 and z's anything, and that looks in this picture. So that implies that we actually get not really a surface anymore, a degenerate case, we just get the z-axis. So that particular level surface is a bit unusual, as in it's just a straight line, which my line's very not straight unfortunately, but yes, it is a straight line and it happens to be the z-axis. So what's common between all the surfaces available? They all of them have a centered around the origin. They all have a central axis of the z-axis, all of them, including this special case. K equals 0 is just the axis itself. As k gets bigger, as k becomes positive, becomes hyperloid of one sheet, and as k increases, it's the same sort of shape, except it's expanding in the xy directions, where the radius is increasing by proportionally to the square root of k. So that's a bigger answer. That sort of description is what I was looking for, or something along those lines for the full marks. And the question did consider one particular level surface in particular. So if you at least get that one, a bit more of a concrete case, you might go on. So if you could at least go, oh, that's a hyperloid of one sheet, that shows some sufficient understanding, and certainly worth more marks. The tricky bit, I suspect, would be capturing the special k equals 0 case. So any questions, fire away, but that's one of the ones I wanted to cover. The other question that the marker said people had issues with was question 3, part 3. So this is the implicit differentiation question. So you've got a function of 3 variables, and you have to try to find some implicit derivative. You could do it implicitly, presume it's the mechanism you taught in Maths 101. The easy way, I think, to do this is to first rearrange it to put everything on one side. So x squared minus y squared minus zy plus xy is 0. And we call that function g. And then the implicit function theorem says the partial derivative of anything is the big minus sign, easy thing to forget, of the partial derivative of whatever corresponds to the bottom, so g1 in this case, divided by the partial derivative of whatever's on the top, z in this particular case. And taking partial derivatives directly is much easier than trying to do anything more implicitly. So if you take partial derivative of this with respect to y, x squared derivative gives you nothing, minus y squared gives you minus 2y, yz gives you minus z, and plus xy derivative gives you plus x. And the bottom, take partial derivative with respect to z, nothing, minus y, nothing. And then get rid of this, make the minus signs match up, and that's sort of the answer. So in this case, so x minus 2y minus z over y is essentially that particular partial derivative. And so the key thing I used here, which I think, although certainly I find easier, is the implicit function theorem. And the key, so common mistakes that people normally make of this sort of stuff is they forget to rearrange. You can see that you need to rearrange first to put everything on one side. That gives you sign errors. The other mistake sometimes people make is they forget the minus sign there. So I'm not sure how you went personally, but they were the two most common errors. So as I said, people really did very well on the assignment in general, which is great to hear. So I just want to cover those things off in particular. So now to the main event. If I can find it, here it is. So what we're looking at going forward now is looking at how to do integration of functions when you've got more than one variable. And we learnt last week how to do double integrals. That's pretty much what it is. You've got two variables around. And we looked at double integrals of a special type just over rectangular regions. So I want to generalize it to more complicated stuff. So I think it's good, if I zoom in a bit, just to talk about the basic plan of attack. This is the basic plan of attack. So we want to try to draw the region of integration. Now, in general, you don't want to try to draw we want to draw just the 2D region that we're integrating over. So last week was just rectangles. Here they'll get other things, but it's really helpful to give you an idea what to do next. When you've drawn the picture, then you can recognize what sort of type it is. So if it's a rectangle, fantastic, and you do that one straight away. There are some standard forms called type 1 or type 2 regions, which I will elaborate in a second. There are some standard forms of polar coordinates, which is pretty much anything with circles or bits of circles, like annulus and ring, that sort of stuff. So if you draw the picture, oh, hold on a sec, that's just a bit of circle, that's really important to tell you what to do next. So I think drawing a regulation is really helpful to diagnose the next step. So once you recognise the standard forms, okay, if you recognise the standard form directly, just run away with it. If it's not one simple standard form, you might have to split it up in bits which do have standard forms. That's certainly a more substantial question, which I will avoid wherever I possibly can in the subject, and that's true for the exams too. So you wouldn't normally expect it to do that, but try to think of an alternative way. And then once you've worked out the standard types, just approach each of them directly. And the basic way is to do them as an iterated integral, effectively. So that's the basic plan of attack. There is one more advanced method that I haven't mentioned yet, and that is the idea of transforming the variables, which essentially is integration by substitution in this sort of context. It's a bit more complicated because you've got more variables present, but that's the basic idea. And that's a way of transforming a region. So if you had full control, that allows you to get a region which is a bit awkward to try to deal with, like one that required a lot of splitting, for example, and allow you to transform into a much nicer region. So we'll do that next time we have a meeting, and that would be after Easter. So we're going to have a bit of a break in lectures, just coinciding with the internal class having a break. That allows you to go forward or to catch up, as the case may be. So that's the basic plan of attack. So I guess what we need to spend some time now is recognizing what the standard forms are. And so I want to look at each of them: type 1, type 2, and polar. So the first ones are called type 1 regions. Knowing the difference between type 1 and type 2, the names, I don't really care about the names as such. But it's important, they are very similar to each other. So pretty much, they are regions where the y is bounded between two functions of x, and x is bounded between two constants thereafter. And these are some example pictures of them. So one type is you've got two functions of y, two functions of x, bounding it, and you just cut off each end. It can be that they meet as a point, or one meets a point, one doesn't. These are sort of three examples you can see here. And when you have that sort of case, the way to approach them is to basically write as an iterated integral, just integrate the y value first between the two different functions of x. Then once you've evaluated that and sub the limits in, then integrate with respect to x between the two constant values. Some tricks with this here is when you sub in the limits, you get more x's cropping up, so you have to keep track of that. I can see someone's trying to come in or not. I hope you can hear me yet. So that's the basic idea. So when you've got a type 1 region, then it very naturally translates into doing the functions of x on the inside, and then the constants thereafter. So let's have a go at one question. I can see someone's trying to type. I might not respond straight away, but it's all right. Okay. So here we're considering a region. So pretty much what we're considering is some sort of thin plate out there, and it's given mathematically by being bounded between two different curves, which I'll have a quick draw in a second. If it's got uniform density of, say, 1 kilogram per square meter or whatever it might be, let's work out the x-coordinate at the center of mass. And so you can use double integrals to work out all sorts of things. And this is one of the things I want to show you in this case, is that you can use it to work out the balancing point. So the center of mass is, if you put your finger under the center of mass for this little plate, you could balance it on the finger. So, as I said, the plan of attack is, given a integral of any sort, the first thing to do is just try to draw roughly what the region of integration is. And that really corresponds to drawing this region R. So let's draw my axes, x and y. So I've got the function y equals x squared, and the function y equals x to the 4. So when between 0 and 1, at least, x to the 4, you screen small numbers, so they get even smaller. So x to the 4 is just a flatter version, so I'm exaggerating a lot. So y equals x to the 4 is down the bottom, and they meet when x is 1, and y equals 1 for that matter. So this is 0.11. So, as written, we notice, so when we see that, you can see that this, as drawn, it ends in 2 points here, but basically this region is bounded between a curve of x on top and a curve underneath. And so therefore, if we integrate between these two different curves, if you integrate between these two different curves first, that considers a type 1 region. So this is a type 1 region. It's also other things, so it's, as we'll see in a second, it's happened also to be a type 2, both at the same time. But now we know it's type 1, that gives us a strategy for how to integrate it. So when drawing the picture, you go, oh, I can see it's between these two functions. Also, the picture tells you what the functions actually are. So now we know what it is. There's a constant we can leave out the front. We're going to integrate between these functions first. So we integrate the y value first between these functions. And the bottom function for my picture, I can see is x to the 4, and the biggest function is x squared. And then the x values range from 0 up to 1. So they would become the limits for x as the outside ones. And what I'm trying to integrate here is x. So let's pause for a sec there. There's a bit of work to get to that stage. So when I'm trying to face with any old integral, I first draw my region of integration, look at it to try to work out what type it is. In this case, I can see it's a type 1 region because it's bounded between curves. Then I write down my limits. I integrate between these two curves first, which in this case are different y values. That's why it's dy on the inside. And just put the values of the function on the limits. And then work out what the limits for x are again from my picture. Now once I've done that, done all that process, then the rest is just doing it as an iterated integral. I just really do the inside first, and then do the outside. So I've just copied all the outside bit down. I'm not really doing that yet. So I'm going to integrate the inside. So integral of x dy, well, x is constant with respect to y, so it just becomes x times by y. And then I sub the limits in. I could just run x to the 4, but because there's lots of variables floating around, I just want to make it clear. I'm subbing in y equals x to the 4 and y equals x squared. So again, all the outside doesn't change. Then I sub the limits in. So if I sub in y equals x squared, I get x times x squared, or x cubed, minus summing x to 4 gives you x times x to the 4 gives you x to the 5. And that just does the integral inside the limit. So now we can repeat again. And so when we repeat a second time, this is just a single integral, which we know how to do quite well now. It's just one variable. So you've got x cubed on, so x to the 4, I should say, on 4, minus x to the 6 on 6, between 0 and 1. Sub the limits in. You get a quarter minus a sixth. So that's 3 minus 2. 15 on 12. That's it, right. 3 minus, no, on 24, I think. Please correct me if I'm wrong. So after a little bit of use a calculator, maybe is what I should be doing, you get something like 15 on 24, which does simplify to 5 on 8. So 5/8. So what that does, it says that the balancing point for x happens to fall at x equals 5/8, which will be about there in my little x on the picture. So if you imagine it's just imagine a piece of paper in this sort of shape, maybe a piece of cardboard, I should say, in this shape, which is rigid. Then this sort of integral is working out the balancing point. So you could put your finger under that part of the cardboard, and you better balance the whole cardboard on it. That's the idea of a center of mass. I'll show you these sort of formulas later. So that's the a type 1 region. A type 2 region is pretty similar, is that instead of y being between two functions of x, it's just x being between two functions of y. And you can see I've drawn some examples here. And in that case, you do it really similar. You just go, well, x is between the functions. You do that first. So integrate the x part first, and you integrate between its two functions of y, the inside and then the outside. So really similar. So let's do almost the same example. So this is almost the same example as before, so exactly the same region as a matter of fact. But this time we're going to work out the y coordinate center mass, so it's just a slightly different integral. So if I draw my picture again, so y equals x squared on top, y equals x to the 4 on the bottom, and that's so the thing to notice is that although yes, the function is between two functions of x, we can also consider it in the opposite direction, so not up and down, but really between the bottom function here, which if you make x the subject, x would be the square root of y, is what that particular function here, that's the bottom of in that direction, and in this function here we can also is x the function of y, and that would be x is the y to the power of a quarter. So we can see this region not just as a type 1 region, but also as a type 2, and that is x is between x is being two functions of y. And not all regions are type 1 or type 2. You can certainly get neither of them happening. They can be neither. Worst case scenario is you can always split it up into cases where it is So unless you've got something absolutely pathological sort of curve, but so you can always split them up break them up in enough pieces for it to work. There are some times, like you can see here, where it's both type 1 and type 2. And in that situation, when you're drawing it, you can choose how you'd like to do the integral. So in this case, I could do it as a type 1 from match like I did a second ago, or I can treat it like type 2, which is what I'm going to do here. When you have that choice, one way might be a lot easier than the other way. And so when you're doing it, it's good to think, well, which is going to make it easier for me? Sometimes one way is much, much easier than the other. And so sometimes you actually can change the limits to really help to benefit you greatly. But more on that next week, or next time I should say. So in this case, we're recognising as a type 2, so we integrate x first and then y next. So x is between two functions of y, and the bottom, so the one that comes from the leftmost curve, is the square root of y, and the one that comes second is y to the quarter. So they're the bounding curves for bounding functions of y, and then x would go between 0 and 1. Sorry, not x. Y would become between 0 and 1. So same result, just look at the wrong axis. And then you approach it the same sort of way. So you know y. So why you do this was a type 2 rather than type 1 region? If you notice, the inside integral has a y there. Y is completely independent of x. So when you're integrating the first bit, the inside bit here, the y is even sort of independent. You can just leave it at the front. So it's really, you're really just integrating 1 to give you x. So doing as a type 2 region rather than type 1 region makes the inside integral easier in this instance. Not heaps easier perhaps, but certainly easier to do. And that would be why, that's maybe one reason to do it. So if you then carry forward, so if you sub in these two things, y is a quarter, y equals half, you end up getting y equals 5 quarters minus y to the 3 and 2 to y. And it's much easier to write it all in one simple power. And then approaches per normal. So integrate the power, add 1 to the powers, divide by the power, to y to the 5 and 2 and 2/5. Sub in 1, you get 4/9 minus 2/5. Sub in 0, you get nothing, and whatever that's equal to. Should be a bit lazy, is that, isn't it? So it's 20 minus 18, so it should be a third, I reckon. That's the answer. So in this case, doing it that way meant that the x integral was always nice. You could swap them around. In this case, you could handle it anyhow. It's not that difficult. But noticing that flexibility is helpful in some circumstances. So look out for both of them, I guess, is the moral of the story. In terms of what we did, this is a picture of the curves drawn more accurately than I did. So you can y equals x squared, y equals x to the 4 as the two curves. We worked out the center of mass, so that's a little square highlighted there. You might see it. See it? So we've worked out that particular coordinate for the center of mass in the middle there. So you can see the y value is about a third, and what's that we worked out? And 5/8. So 0.625 is the x coordinate. you can, just as an aside, you can work out all these sort of integrals in Maple if you're interested. So there is an appendix to Chapter 2 towards the end, how to use Maple for various stuff. And so here are the commands here. Just a word of warning, if you want to try them out, or you can try them out from this slide here, the hat characters, those ones just there, don't copy nicely from PDF into Maple. The PDF document uses fancy fonts to make them look pretty. The problem is that's Unicode, which doesn't translate properly into the hat character on your keyboard. And so what that means is that when you're copying and pasting this into Maple, you have to retype the hat characters yourself directly, and same with quotation marks at times. And that's just a font issue with PDFs. But you can see that there are, to specify integral for a type 1 or type 2 region, pretty much is you have to use the vector calculus library, integral of integrand, and you say x and y, you have to give a region and limits for x, limits for y. And if you wanted to do the way around, like we did type 2 region a second ago, you have y comma x. So they're the various limits, integrals we just did. So last of the sort of standard types is bits of circles. So the three standard types are type 1 and type 2 regions, and rectangles are special cases of both of those, technically. The next special type are bits of circles, essentially. And so what I mean by bits of circles, it could be a whole circle, or it could be a semicircle, or it could be a segment of a circle, or it could be an annulus, which is the difference of two circles, or a bit of an annulus, something like that. So these are all different segments of circles. So when you've got that, then a key way of doing it is to use what's called polar coordinates. And polar coordinates is pretty much doing the substitution, letting x be r cos theta and y being r sin theta. When you do a change of variables like that, it has other impacts. It certainly changes the limits. And so you need to think carefully what the limits for r and theta are when doing so. A useful trick is if you ever see x squared plus y squared ever, then that can be written down as r squared. That's consequence of the first two bits, but that's important. Because you're changing variables, it changes the bit of the area. So the dy dx term, which we commonly write as dA, ends up becoming r dr d theta. And you can do d theta dr if you wanted to as well, of course. So that's the key thing. So we'll look at more about change of variables. So this here, so the r is a special case of the Jacobian determinant that we'll look at later. But it's important formula. So it's useful in its own right, and you don't who knows where you may not know where it comes from initially, but you can do it out. The answer is the formula is not nearly as bad as you think. If you've got a bit of a circle and you want to split up a little segment like this, I'll just zoom in. So a little segment looks something like this. This bit here is a curve, and so the length of this curve would be, if I just draw some dots down, would be the radius times by the angle between the two. And so if you've got a really small angle, the length of this bit would be r d theta. That's just the length of a bit of a segment of a circle. The width here would be the difference of the radiuses between the outside and the inside bit, so it's dr. And so this small bit of area, if you make theta is small enough, it gets closer and closer looking to a rectangle. So it's so a small bit of area would be approximately equal to r d theta dr, just the product of the two. And if you make it small enough, so I take the limit, so the limit would be differentials, it's true. So the d, one of d is just the limiting idea. So that's basically where it comes from. So let's have a look at an example. What you do. So, although I've mentioned collar coordinates, the strategy is actually the same, and that is you would never think about collar coordinates necessarily the first. So you've got a thing. First thing to do is try to, rather than tackle it, is to draw the region of integration. Even when the limits are specified, as they are here, I would still draw a picture. So this is trying to say that the inside limit's pretty much saying we know that y is between the top one, root 16, make that a 4, make it doable. Just realised my mistake. So y is between these two curves, and x is between 0 and 4. That's what it just translates to being. So if you draw pictures, we know x is positive, going up to 4. What does y equals the square root of 16 minus x squared look like? Do you know what it looks like? So, Naomi? Yep, so it's a semicircle. Radius 4. So it looks like that. So we'll go up to 4. We'll keep going around, of course, but we're only concerned with x between 0 and 4, so we'll just focus on the bit that we got on. And the minus case would be another semicircle down the bottom. And so the region that we're integrating over would be this right semicircle. And as soon as you draw this picture, as soon as you realise, oh, it's just a bit of a circle, that tells you that polar coordinates are a good idea. Other hints for polar coordinates is whenever you see things like square root of a constant minus x squared in any of the limits, that reeks of circles, and you're thinking, oh, maybe a circle's a good idea here. So now you know you got polar coordinates. Basically, I would write, x equals r cos theta. So let's do it in model. Actually, if I see any x squared plus y squared, I'll write down that r squared first. That's the first thing I do. If there's any other x's floating around, I'll write it as r cos theta, and y equals r sine theta. So that's changing the integrand. So the integrand here is the square root of 1 plus x squared, and as soon as I see that x squared plus y squared, I'm just going to write it as r squared. So I'm doing this one straight away. Next thing I want to do is I want to change the differential. So the differential with short row is dA, but as you can see here, it's either dy dx or dx dy. So just come over to the dA part, and I'll translate that to r dr d theta. To r dr d theta. And it's good to end the square root just as I've written in this case, just to split them out. So that's the translation. Next, I need to work at the limits, and the easiest way to do this is with the picture. So because I've written r in the inside, I have to specify the limits for r first. That's just the different radiuses. So the smallest the radius can get of a circle would be nothing at all. That's like the origin here. And the largest it gets is this outside one, which has a radius of 4. So r goes from 0 up to 4. Next one is theta, that's the angle. So the angle, so r is that direction, so it's the radial, how far, a radial direction. Theta is the angle from the positive x-axis. So what are the limits for theta in this case? So the biggest it would get is all the way up to this point, that's the maximum. And the smallest would be all the way down here, which would be a negative number. So Naomi, any ideas what the limits for theta might be? You can say no, that's okay. Yep, so the largest it gets is pi on 2, and the smallest it gets would be minus pi on 2. And then it's just a matter of approaching it just like any other iterated integral. Just some comments about this particular example. So I'm going to do it a slightly different way. If I look at the integrand here, I can say I have no thetas at all present. And indeed, the limits have no thetas either. So as a matter of fact, we've changed it from integrating from a semicircle to integrating over a rectangle, as a matter of fact. And so when both the limits and the integrand are free from thetas, I can factorize things out. So I can factorize this d theta out the whole thing. So what I'm left, so it's not factorizing, this is called a separating of an integral. So when the integrand and the inside limits have no impact on the other one, I can sort of separate the thetas completely out. And what I'm left with, I've still got the integral of r's in the middle. I'll just change the order just for convenience sake more than anything else. But this is the idea of separating an integral. It's separation. And you see separating variables when you're doing, you see that sort of idea in other circumstances like differential equations, for example, which you might be doing in your other subject. So now we've separated. Let's persevere as it is, and separating when it's possible makes it easier in my mind. So if I integrate the thetas bit, integral of d theta, which is implicitly a 1, will become theta between pi and 2 and minus pi and 2. And if you sub those limits in, you get pi for that part. The second part is we're going to integrate r square root of 1 plus r squared, which you can do via substitution. So you could do substitution u equals 1 plus r squared, or you could do it by observation. And what I mean by that is the derivative of the inside here is 2r. So I'll just manufacture a 2r. And so the square root of the inside is 2r, and so it's called integration by observation. So if I integrate 1 plus r squared to the power of a half, that means I raise the power by 1 and divide by the new power, and then sub the limits in. Now, just before I sub things in, is that okay? I mean, for some people, that's skipping heaps of steps. You can. It's only allowed, so that's okay. Yep. And if you need to, you can. And if you need to, make sure you get the right answer. I mean, for anyone else watching the recording, etc., make sure you get that right answer. So if you need to put the extra steps into doing an explicit substitution, do so. But I am okay with you skipping by observation like that. So if I sub in the numbers, so I'm going to get a third. Subbing in the 4 gives me 1 plus 4 square, which is 5 to the 3 round 2. Minus, if I sub in 0, I just get 1. So the final answer is something like pi on 3, 5 to the 3 on 2 minus 1, which you can write in various ways, but that'll sort of do it. Just to make a point of this, this is maple here, which I should make bigger. So I'm going to get maple to do this question. So in order for it to do the fancy double integrals, I need to say with vector calculus. Then I want it to do an integral of the square root of 1 plus x squared plus y squared. Now, as written, it was x and y values specified as a region. So specified as a type 1 region, as a matter of fact. And so the values for limits for x was 0 up to 4, and the limits for y was minus the square root of 16 minus x squared up to the positive square root of 16 minus x squared. So that's pretty much what the question is written. So if I press enter, it churns away a bit, and this is what the answer that Maple gives. If you look at it, basically it's had a hard time working it out. So I've had a hard time and actually has not given an answer. But what it's done instead is it's had to split up. It still hasn't been able to integrate. It's done the inside integral okay, but it hasn't been able to resolve the outside integral. So I can work it out numerically because it's got stuck. So if I do a val f of the previous line, I can get a numerical value. So I can work it numerically, but it hasn't been able to work it analytically. So it hasn't been able to get it the exact answer. You can get it to do using polar coordinates, so you can integrate x squared plus y squared. And you're going x and y. You can say it's a bit of a circle, so it's a sector, I think is the word. So you want it's a bit of a circle. The circle with the center at the origin and radius 4 between minus pi on 2 to pi on 2. Okay, so I'm integrating over a bit of a circle, the sector bit. The circle it's a bit of is that one there, so center and the radius, and it's the between these angles. Whoops. And I need to press a comma there to make it work properly. And this time, Maple has been able to work out the answer, which is not what I got, which shows you why I made a mistake. And if I do a val f percentage, I did actually get the same answer as before. So it is all working. So Maple can work it. So either way gives you the same answer. It's just that trying to do it directly, trying to treat it like a type 1 region is actually quite difficult. So hard that Maple has trouble working it out. And the reason is because all these different square roots, logs and square roots, that sort of stuff, does actually make it quite difficult. And if you write like this, it certainly is challenging to work out how to do that. The way to approach that sort of integral with all those sorts of things in it would be to do a first get rid of the square root of 16 minus x squared by a trig substitution. Cleans out lots of those sorts of things. Then to get rid of the logs, this is how you do it directly, which is why Maple has trouble. So to get rid of the logs, as written, you'd have to do integration by parts. We'll get rid of the logs for you at that point in time, and then after that point in time, you're then left with heaps of trig terms, which you could slowly simplify down. The problem is the fractions get in the way, so you'd have to use partial fractions to simplify down, and looking at the fractions you probably would need to do a t substitution just to make them doable as well, and maybe more partial fractions. You have to do partial fractions somewhere along the line, either earlier or later. So that's really hard to do by hand. You can do it. You certainly know all the individual parts. It's perseverance is the key thing. So moral of the story is it's better to use polar coordinates sometimes and try to do it directly. Also, the moral of the story is I can't square very well, obviously. and that should be a 17. So the other moral is I make mistakes like everyone else does. But mistakes are okay. Mistakes are good learning opportunities, so they help you learn. So help you remember that. Help me remember that I should be squaring 4, not just adding it on to 1. So that's the main things I wanted to, the theories I wanted to cover today. So the only other thing just talk about is that what do you use double integrals for? And so we've dealt with them as in terms of volumes under a surface is sort of the general interpretation, which I mentioned last week primarily. But there's other applications, which I've mentioned some today already. So you can do area. So the area of a region is the double integral of just dA, so just integral 1 essentially. If you've got a region of a certain density, so like mass for example, so a certain mass density, then the total mass down the bottom here is just the double integral of the density respect dA. And you can have density of other things, so it could be a charge density. To work at the total charge in a region would be just integrating the density over it. And you do that in 2 and 3D too, for that matter. So these formulas are all 2D ones, double integrals, but you'd have very similar formulas approaching for in 3 dimensions as well. Just a triple rather than a double integral. The other thing is to work at center of mass, like I did before. So the center of mass pretty much needs to have different components. So these are the formulas more useful, these are the ones I used before. So the x coordinate of the center of mass is 1 divided by mass, the double integral of x times the density dA, and a similar one for y. I like nice compact vector notations. That's how you write it all in one go. It's easy to have the simplified one. You can also, so center of mass is, as I said, the balancing point. Similar concepts in terms of rotation is to work at moment of inertia. So the moment of inertia is given by this sort of formula. So x squared y squared, all of that together should be x squared plus y squared be in brackets, by the way, times by the density, and that gives you the moment of inertia. And that moment of inertia is useful in working out how far something will spin. So resistances spin, that sort of idea. And I've got the moment of inertia about an origin, but about the origin of the other things here too. So just help lock these things down. I'll just do partial examples of some, and in doing so I want to mention a few other tricks. So don't have it. So in this case I'm integrating over a triangle which has got the vertices x equals plus minus 2 and y equals 2. So I'm just looking at this triangle here. Now I've got a plate, so I've got a piece of metal or piece of cardboard, whenever you want to think about it, in that sort of shape. And I would like to, and we know that the density is 2 kilograms per square meter. So that's actually what my density is. What I want to do is I want to work out the various things. I want to work at the mass. So I want to do it 2D ways. I want to write it as an integral. So broadly speaking, the mass would be just summing up the density, which in this case is 2, times by the area. And because this is a type 2 region, this would be, say, it's basically between two functions of x. So x is y minus 2, and x is 2 minus y. Are the bounding curves? So I'll just spell the first one out only. So it's integral from y minus 2 to 2 minus y, and then the 2 dx, and the y goes from 0 up to 2. And you work that integral out. So one trick though is that the mass of if you've got a constant density, so if this density here, that number there is a constant, this is just going to be equal to the density times by the area. That's a little trick. And that's true for, as long as it's constant density. The area, it's just a triangle, so we know area is a triangle pretty well. So it's the perpendicular height, which is 2, times for the base, which is 4, times a half, gives you 4. So the area is 4, so 2 times 4 gives you 8. So when you are trying to work integrals out, you are allowed to use these tricks, unless I explicitly ask that you work out the integral. And I certainly do that at times. So in both the exam and the assignments, sometimes I say you must work out the integral to get full marks. But even if that's the case, I'd encourage you to use some of these tricks to help check your answer. And I'm mentioning a few in passing here. There is an appendix at the end of chapter 2, 2.6 maybe. I don't know, I'm getting it wrong probably. So there's certainly a section all the end which has some of these sort of common results that you might find useful. You can get away with not learning them if you're pressed for time, but I do think they help you about check your answer. So I do find it's pretty useful. So that gives you the mass of 8, in this case 8 kilograms, for example. So for the center of mass, there's 2 coordinates, so x and a y. So let's just do the x center of mass. So this would be 1 over the mass, which we know is then the double integral of x dA. And in that case, 1 over 8 x dA. And again, it'll be the same sort of limits as before, and you can approach it. One trick for triangles, again, if the density is constant, then this is actually equal to the average of the vertices. So the center of mass is indeed just the average of the vertices. So the vertices are 2, 0, minus 2, 0, and 0, 2. So look at the x coordinates for the moment. So x coordinates would be 2, minus 2, and 0. If you add them up, you get 0. And so the integral actually ends up being 0 in that case. And y bar would be the y coordinate. That would be the average of the y values. So 2 plus 0 gives you 2. Average them, so divide by 3 gives you 2/3. So that would be the average value. And again, if I just draw that on my picture, it's 1. So that's about there. That's where the center of mass is. That will be the balancing point for this triangle. Is what worked out. Next one is the moment of inertia about the origin. That's called I naught. And that's just the double integral. I didn't quite write it before, so let's do it now, of x squared plus y squared dA. Oh, sorry. The density times dA. And there's certain shapes have special formulas for it. A triangle is not one of those special shapes, unfortunately. So at the end of assignment 2, so if you got a physics textbook, if you do physics, the textbook tends to list the moment of inertia for lots of standard shapes, heaps of them. And so your assignment 2 is getting you to derive one of those results. So triangles aren't that special, but certainly bits of circles and cylinders and squares and rectangles all have well-known results. And you could prove any of them using this sort of formula. The last one, so I won't write the answer. And the last one is the moment of inertia about the center of mass. So that would be the basically centering it. So it's x minus the x coordinate of the center of mass squared plus y minus the y coordinate of the center of mass squared. All in brackets. Rho dA. Rho being 2, y bar is 2/3, and x bar is 0, so you can plug them in and go for it. And there are, in physics, nice results relating to these various things. So here it is here. So this is called the parallel axis theorem. So the moment of inertia, I say about the origin, for example, is the moment of inertia about its center plus the total mass times the square distance that you're doing, which happens to be that quantity in this instance. So certainly lots of these sort of formulas crop up in physical quantities. So what I'm trying to press upon you is this stuff is useful. That's what I'm really just trying to sell you as. And these results are needed. People do need to know them from time to time. So how are they dealing with various things? And moment of inertia is really important for anything rotating. Center of mass and mass is really important to any other movement. So if you've got a complicated object moving through space or on a plane or whatever it might be, if you understand what happens to the center of mass, and understanding how it spins, then you have a fairly good understanding what's happening. And so you can summarize a quite complicated shape really by two key ideas: center of mass and its moment of inertia, etc. So that's all I want to cover today. So please have a look at assignment 2. You can't do it all just yet, but if you look at the beginning of assignment 2, it just lists a bunch of double integrals, and some are easier and harder than others, but there's a sort of mix there. So what I encourage you for all of them is just to try to draw that region of integration to begin with, for every single one, and start looking for some of these standard types. So you might go, oh yeah, I can see it's type 1 or a type 2 region, and bang, that's straight away. I might go, oh, that's just easy done as a polar region. So the two tricks I haven't really mentioned yet is swapping the order of integration. So I mentioned that in passing last week, but I want to do it again next time. And also the other thing I want to trick is the idea of transforming variables. That particular question sticks out like a sore thumb because it's asked quite differently. But that's certainly a plan of attack for how to do it. So I encourage you to do that. So if you have any other questions, you can fire away now. But otherwise, I'll see you in 3 weeks' time after the break in lectures. But please continue working. Either catch up if you need to, or move forward. It might be you can read the rest of the material and have lots of questions for me next time about the extra 2 bits on double integrals. But anyway, thanks very much for coming.